How I would like to proceed with what is state feedback and what is controllability and what is observability. State feedback is nothing but a feedback of the system which is taken from the state variable. That is called state feedback. And what is the effect of this feedback on controllability and observability as well as stability? Yesterday we had a small derivation also. The derivation that I would like to show over here. Let us see this one. Coming to this one, if we consider overall system with a number of multiple input, multiple outputs, then we have to know that the state equation we can write x dot of t is equal to a into x of t plus b into u of t. Y of t is equal to c into x of t, right? Now, we can write this overall equation by using control law. What do you mean by control law? Yesterday we had a small discussion. So whatever the input obtained in the given system from the reference input as well as feedback taken from the state variable, then we can call it is control law. So what is control law over here? See here I am going to, let us take R is multiplied with n. Let us consider where n is a constant. Let this block is included over here. Then I will get u of t is equal to, that means u is equal to, I can write u is equal to r of t or r into n minus what is the value appear over here? That is k into x. That is k into x. So let us see this one. We're coming to this one. Based on that equation, we can write a control law equation based on the diagram. So that I can write u of t is equal to n into r of t minus k into x of t. So in which r of t is a new reference input signal. The matrix k is called state feedback gain. That is yesterday we had discussion. And n is a forward path gain. Let us see this one. Now substitute that equation u, that is a reference input into the open loop system, gives a closed loop state equation. Yesterday we had discussion. That is x dot of t is equal to x dot of t, right? X dot of t is equal to a into x of t plus b into u of t. Let the open loop system overall transfer function. Let I am going to take it is equation 1. Output equation which is not affected due to this state feedback. No need to take this output equation. Let us coming to the next with reference to after connection of state feedback, the equation of the given system, that is input equation with respect to reference input is given by equation number 2. Now substitute equation 2 in equation 1. Already I did this derivation part in the previous class. Let us going to recall the same derivation with the mathematical expressions. Okay. So substitute equation number 2 in equation 1 in place of u of t. Now what would be the change? That is x dot of t is equal to a minus b into k into x of t plus b into n into r of t. And there is no change in the output equation. Y is equal to c into x of t. Now obviously the closed loop system, the given linear time invariant system is R is multiplied with the forward path gain, that is n. B, we already know that, which is multiplied with the planned input. Now this is a x dot. If we integrate this x dot with respect to x dt, I will get it. State variable is x. Now let the feedback with the matrix A over here. And there is a one more feedback element we are going to assume, that is a closed loop feedback with respect to gain constant k. Now this gain constant and this connection is called state feedback. Now x is multiplied with c, so that this dotted line indicates state equation before connecting this state feedback. Without connection of state feedback, there is a state diagram for the state equation. That is for equation 1 diagram. So after connection of state feedback to the given system, now the overall diagram is corresponding for equation number 2 diagram. The entire system block diagram represents equation number 2 systems. Now let us take this type of control is said to be static because U only depends upon the present values of the state variables X. The reference number, reference input is R. Note that it requires that all states of the system is to be measured. That we can see in the next. So in this part, we have to see what are the changes after connection of this state feedback. What are the observations we have to measured over here. So I hope you understand. Without feedback, let equation 1. Let us substitute or let us consider a state feedback. After substitution of equation number 2 in equation 1, we'll get one more state equation, that is a closed loop transfer function state equation. This is equation number 3. This is very, very important. This is a new state equation after connection of state feedback. That is, in place of A matrix, we will get A minus B into K. So that what would happen? What is the after connection of state feedback? What are the changes? Let us see this. Now the techniques for the design of the state feedback gain K to achieve, that is, what are the techniques are used to design a state feedback gain K to achieve? What are the achievements? After designing this K value, what will be the changes? Let us consider. The first one is a pole placement. That is a stabilization. That is where the poles can be placed, which is decided by the value of gain K. So before connecting gain K, the poles may be located right side or left side or on imaginary axis. We should not change it. But when you consider this gain constant K, that's a state feedback, then we can change the pole place from one place to other place. That's a stabilization. We can change the poles from right side to left side or else vice versa. Now, regulation and robust tracking. Actually, this concept is not included in your syllabus. So now that I'm not going to discuss about this concept. This concept we will discuss at the time of MTech. Now let us come into the what is the next one. The techniques for the designing of the observers. So generally, a state feedback controller and state observer, there are two designers. We are now discussing about state feedback controller, so that I'm not going to discuss about this observer. So this state observer concept will become after completion of this state feedback controller. That time I will discuss. Now let us coming to the concept. Our basic aim in this part of the course is to learn how to design a linear control system by a dynamic output feedback. That means both the state feedback as well as observer to satisfy the desired closed loop system specifications in stability and performance. So what he is going to say, before connection of the state feedback, what is the location of the poles? Based on the poles location, we can say system is stable or unstable. So let us take, before coming to the connection of the state feedback, what is the state equation? X dot is equal to A into X apti plus. That is already equation 1 before connection of the state feedback. After connection of the state feedback, the equation would be changed. So from equation 1 and 3, if you write the characteristic equation, what the characteristic equation says, let us consider the characteristic equation is Si minus A mod is equal to 0. This is for equation 1, characteristic equation. And for if you write after connection of the state feedback, the characteristic equation for equation number 3, that equation can be modified as S into I minus of, in place of A, what is the expression over here? That is A minus B into K. So that I am going to write, this is A minus B K. That is A minus B K mod is equal to 0. That this is from equation number 3. Now look at these two. What is the major difference between two equation 1 and 3? Here we have Si minus A only. Here Si minus of A minus Bk. So here the main difference between both the equation is the value of K is to be included. If I take K is equal to 0 over here, that's a gain constant matrix K is equal to 0, then the matrix equation for both 1 and 3 will be equal because Si minus A is equal to 0 in equation 1. Here also Si minus A mod is equal to 0. That means without considering the gain K, both the equations are same. But if we consider K is equal to some values, let the K vector is always row vector, let 1 and 1. Now after substitution of K is equal to 1 over here, definitely the location of the poles can be changed. That I would like to explain in the next slide, how the poles location can be changed from one part to other part. That we are going to check in the next one. Previously, I'm going to explain. Right. Next, I'm going to explain. So let us coming to over here. Let A is equal to 1001. Let us assume that. Now, if you find the roots of this polynomial, the poles may be located somewhere. Similarly, if I substitute K is equal to 1, 1 and B is equal to 1, 0, then the location of the poles may be changed. Then the location of the poles may be changed. That is, we can get a stable system. There is a one important beauty of this state feedback controller is before connection of state feedback, the system may not be controlled or may be controlled. But the beauty of this state feedback is after connection of state feedback K, the system definitely comes into the controllability. The system will comes into the controllable. That's the main concept. That is, the system is said to be before connection of the state feedback is uncontrolled. When you connect the state feedback, the system will become into the controllable. That's the main important thing. Or we can control the stability of the system also. Suppose before connection of the state feedback, the poles may be located in the right side of the S-plane. When you connect the value of K, the system will become into the stable. That is by connecting the value of gain constant K. So that's the main important thing. And K value consider చేయకముందు system unstable అయితే ఉండొచ్చేమో కానీ when you connect to K value, automatically system will become stable. Or also we can become the stable system into unstable system based on the value of gain constant K. But the system is not controllable. That not controllable system can be controlled by controlling the value of gain constant K. అంటే K value మీరు కనుక మార్చుకొని కనుక సబ్స్టిట్యూట్ కనుక చేస్తే the system will become controllable. That we are going to see in the next one. So that here I would like what he is going to say in this marked one. Here we are going to use this state feedback and to obtain to satisfy a closed loop control system stability and its performance. Okay. Now let us consider here we start with a single input, single output system. SISOM means a single input, single output system. And then move on to multiple input, multiple output system. Over the end of the course, we will discuss some optimal designs. Now let us see what are the changes. So here we start with the single input, single output system. Let us take the state feedback, the control scheme with the forward recomposition. For simplicity, let's assume that the forward path gain I'm going to take n is equal to 1. You may take the n value or you may not take n value. It's not an issue. No need to take. There is no problem at all. So when you take n is equal to 1, this is a reference input, R is a reference input over here. U is the plant input before connection of the state feedback, where B is the input matrix. So multiple of U and B is, we know that B into U over here. And this is a x dot of t. So integral of x dot of t is nothing but x. This is a state equation. So what is the mark over here? This is corresponding to the before connection of the state feedback, which is called equation 1, state equation. As well as here we are going to connect one feedback with respect to K, that's the state feedback with respect to reference input. So an essential system property is the state feedback is controllability. And our first important observation is that controllability is the invariant with respect to the state feedback. That means we are going to prove this one. So what is the theorem here? I am going to take. No need to explain, no need to write this theorem. We just note down the, how the system will be controllable using this state feedback. Let us see this one. For any value of k, the pair a minus bk and b is controllable. That means if we take k value is any value of k, the k value should be the 1 by n number of rows matrix. 1 by n matrix. That is, the k value is always row matrix. That means single row and n number of columns. That it is k1. That the first element is k1. The next element would be k2. The next element would be k3, and so on. N number of k values are there. So on, n number of k values are there. So therefore, the pair a minus bk and b is controllable, because to satisfy the controllability of the system, we have one composite matrix. What is a composite matrix for the controllability? That means QC is equal to, there is a formula. What is the formula over here? The first matrix is B, and the next matrix, row matrix, column matrix would be A into B. The next matrix would be A square into B. The next column, the matrix is A cube into B. A cube into B. Like this, the matrices will be obtained. It's a composite matrix. So to form the composite matrix, we need to have both the matrices, B matrix as well as A matrix. But after completion of, after connecting this state feedback, the new model can be changed. That is, A matrix is replaced by A minus BK, and the B matrix is same. So therefore, here the composite matrix formation will be different after connection of the state feedback. That I would like to show in the next slide. So therefore, what he is saying, for any value of k, the pair, that's the matrices A minus BK and B is controllable if and only if the pair A and B is controllable. If and only if the pair A and B is controllable. This is what we are going to show in the next one. Next, continuation of the same theorem. It is interesting to note that, on the other hand, observability, he is going to say about observability. It is not invariant with respect to the feedback. It is not invariant with respect to the feedback. Let us see the small example. There you can understand what is feedback element, how it is going to be verified whether the system is state controllable or not controllable or observable. Let us see this one. Let us take a small example. I'm going to explain this one. Let the system with a state equation x dot of t is equal to 1, 2, 3, 1, x of t plus 0, 1 into u of t, and output y of t is equal to 1 to x of t. So is controllable and observable, since it is controllability and observability matrices. So that first we need to check whether the system is controllable or observable. So that as per the previous discussion, to find the controllability, we need to form one composite matrix, that is QC is equal to, what is a matrix? I'm going to write the QC matrix is equal to, the first element would be B, and the next element would be A into B. Because it is a 2 by 2 matrix, that's a system matrix is 2 by 2 matrix, therefore its order should be 2 by 2. So what is the matrix QC now? QC is equal to, I can write, what is the matrix B? Matrix B is 0, 1. This is a matrix A, this is a matrix B, this is a matrix C. So what is the B matrix? It is 0, 1. What is the matrix of A into B? That's multiply matrix A and B over here. I will get the resultant vector, because it is a 2 by 2, it is 2 by 1. Finally, the matrix order would be 2 by 1. So 1 into 0 plus 2 into 1. What is the value? It should be 2. Should be 2. What is the next element? 3 into 0 plus 1 into 1. It should be 1. This is a QC. Now find the rank of this matrix. What is the rank? To find its rank, we need to find a determinant of this composite matrix QC. We need to find this determinant matrix QC. If QC is not equal to 0, then its rank to be 2 and it is equal to order of the system, then the system is said to be controllable. What is the determinant of this matrix? It should be 0 into 1 minus 1 into 2. It gives minus 2 and which is not equal to 0. Therefore, its rank should be 2. Its rank should be R is equal to 2. So therefore, the rank is equal to order of the system because the matrix order is 2 by 2. Therefore, the given system is said to be state controllable. The given system is said to be state controllable. It is controllable. Coming to the observability testing. So what is observability? Let us see this one. Now I'm going to use the same matrices to check observability of the system. Here I'm going to again form this composite matrix for the observability based on the matrix A and C matrices. Let us see this one, how we can see now. Let us x dot is equal to this matrix A, that is already mentioned. This matrix B, this matrix C. So to find observability matrix, so we need to have one composite matrix. Q naught is equal to, there is a formula. What is the Q naught? The first column of the element, first row element is C, and the next row element would be, what is the next row element? C into A. Therefore, I can multiply, C is multiplied with, sorry, small one call, important call. Sorry for the inconvenience. So after getting this composite matrix Q naught, let us take this observability matrix Q naught is equal to C, and it is C into A. Let us find the values of C and C into A matrix. So what is a matrix C? It is 1 into 2. Therefore, sorry, 1, 2. This is 1, 2. What is a matrix multiplication C into A? Now it is a 2 by 2 matrix. It is 1 by 2 matrix. So this is 2 by 2. And this is 1 by 2. So how is possible? So C is multiplied with A. Therefore, this 2 and this 2 will be cancelled. I will get 1 by 2 matrix. Therefore, what is the value now? So 1 into 1 plus 2 into 2. What is the value? Let us take this is multiplication. C is multiplied with A matrix. That means here is the 1, 2 matrix. And the matrix A would be 1, 2, 3, 1. Now look at this one. What is the value appear in the first one? That means I can write in multiplication. So 1 is multiplied with 1 plus 2 into 3. That means it gives 7. That means 1 plus 6. Again, 1 into 2 plus 2 into 1. That gives 2 plus 2. So 4. Therefore, the matrix row would be 7, 4. Look at this one. This is the observability matrix. Again, we need to check whether the system is observable or not. That time, I would like to go to again rank of the composite matrix. What is the rank of the composite matrix Q naught? Again, I need to have to find determinant of the matrix. So what is the determinant of this matrix? So multiply 4 into 1 minus 7 into 2. That means I will get minus 10 because 4 minus 14, which is equal to minus 10 and which is not equal to 0. Therefore, what is the rank of this matrix Q naught? It should be 2 because the matrix order is 2 by 2. Therefore, the rank is equal to order. I can say the system is said to be state observable. That means for the given system, it should be satisfied both observable as well as controllable. That means the given system is both state controllable and observable. Now let us see what happened when you connect a feedback to the given system, to this entire system, how it will be changed. That I am going to explain now. What will be the changes over here after connection of this feedback? Let us coming to this one. Here I am going to take one feedback. U of t is equal to R of t minus k into x of t. Let the feedback gain matrix. I am going to take 3, 1 because here we are discussing about 2 by 2 matrix. Therefore, the value of k should be always equal to 2 elements. Let the first element is k1, the second element is k2. Suppose there are 3 by 3 matrix, again I will go to one more element to be added, that is k3. But here no need to add k3 because it is a 2 by 2 matrix. Therefore, the values of k matrix would be k1 and k2. That is always depends upon the order of the system. So here we are considering 2 by 2 matrix. Therefore, I will take k1 and k2 values only. Next, I'm going to take the k matrix should be k is equal to k1 is 3 and k2 is 1. I'm going to take this k matrix. K is equal to 3, 1. I'm going to use the state feedback with the values of 3, 1. When I use this k value, what would be the new changes in the equation? Here he has written a complete direct equation. Let me show. I can show the simplification after substitution of this one. Let us see this one. So after state feedback, what is the state equation again? That means x dot is equal to, that is from equation number 3. We already shown x dot is equal to, what is the matrix after connection of state feedback? K minus E is multiplied with K Vx plus again B is multiplied with the reference input R. That is a matrix A here, A minus B into K. This is what we are going to replace. This is a value here. So let us see this one. What is the matrix A in the beginning? The given system, what is the matrix A? 1, 2, 3, 1. So therefore, the matrix is 1, 2. This is 3, 1 minus. What is the matrix B in the expression? We already know that 0, 1. 0, 1. This is a matrix B. Is multiplied with what? Value of K. What is the value of K? We are assuming 3, 1. So what is the simplification of this matrix now? Because I'm going to do this part only. No need to use this part because we are going to replace this one only. Now, after simplification of this one, if you simplify this expression, I will get the matrix like this. What is the resultant matrix over here? So I will get this is 1, 2. This is 3, 1 minus. What is the multiplication of these two matrices? 0 into 3 plus 0 into 3. What is the multiplication possible? Here is 2 by 1. Here is 1 by 2. This is 2 by 1. This is 1 by 2. So this is cancel. I will get 2 by 2 matrix. So what is the value over appear here? So I will get 2 by 2 matrix. So what is the matrix multiplication over here? Is the first row. So 0 into 3. What will happen? What's the next one? I think it is 2 by 1. It is 1 by 2. After this simplification, 2 by 1 and 1 by 2. What is the matrix appear here? I think the first element would be 0 because 0 into 3 into 0 into 1 is nothing but 0. The next row will also be 0. Now the second one, 1 into 3. I think this is 3. What would be the next one? Again 1 into 3 plus 0 into 1 is nothing but again it should be 1. So if I simplify this one, I will get subtract these two equations over here, I will get 1 minus 0, 2 minus 0, that is 1, 2. 3 minus 3, 1 minus 1, that means the rows would be 0. So this is what happened over here. So here this equation would be complete. This equation would be a minus, this equation is a minus b into a. So what is the change in the previous equation and this equation? Previous equation a value would be 1, 2, 3, 1. After connection of state feedback, what is this equation? 1, 2, 0, 0. So look at stability of the given system also, that I will discuss later. Look at both the equations. So a lot of changes are there. Okay. Now for this value, what is the controllability? What is the observability? That we would like to discuss in the next slide. That is coming to over here. Here it has now the closed loop system state equation would be x dot is equal to 1 to 0 1 into x of t plus 0 1 into e of t. That means this equation is a minus bk value. Okay. Now we have to check the controllability of the given system. The controllability matrix of the closed loop system is here is going to take k. That means we would like to go with our representation. That is controllability composite matrix QC is equal to, let's take this one, the matrix is multiplied with again a into b. But in place of a, what would be the change after connecting the state feedback? Is controllable matrix is equal to QC is equal to here is b. Now a is nothing but a minus e into k matrix, because this is a matrix after connection of state feedback is multiplied with again b matrix. It is also 2 by 2. When you do this one, I will get this matrix is like this. Again, if you find the determinant of this matrix, I will get 0 into 0 minus 2, which is not equal to 0. Therefore, which is a non-singular, then the system is said to be controllable, and the system is said to be absolutely controllable. So, before connection of the state feedback, after connection of the state feedback, the system is completely state controllable for any value of k. K value మీరు ఏ వాల్యూ తీసుకున్నా సరే సిస్టమ్ కంట్రోలబుల్ అవుతుంది. ఒక కంట్రోలబుల్ సిస్టమ్ కి కే వాల్యూని మీరు ఏ కే వాల్యూ తీసుకున్నా సరే the system is said to be controllable. Now the theorem is verified. So the rest of the part we will discuss in the next class after completion of this one. So please, Swati, please send the attendance to me. Thank you.